In the vast expanse of the cosmos, we find ourselves drawn to the skies. Flight, a marvel of engineering and a testament to human ingenuity. At the heart of it all lies the airfoil, the shape that enables heavier-than-air objects to soar. Airfoils, like the wings of an airplane, generate lift, the upward force that counteracts gravity. Lift is a fascinating phenomenon, a dance between air and a solid object. As air flows over an airfoil, it follows a curved path. This curvature, dictated by the shape of the airfoil, creates a difference in air pressure. The air flowing over the top of the airfoil travels faster, resulting in lower pressure. Underneath, the air moves slower, creating higher pressure. This pressure difference is the key to lift. The higher pressure below the airfoil pushes it upwards, while the lower pressure above it pulls it upwards as well. The greater this pressure difference, the greater the lift generated. This is the fundamental principle that allows airplanes to stay aloft. Understanding how airfoils generate lift is crucial for designing efficient aircraft. But the real world is messy and airflow is complex. That's where thin airfoil theory comes in. Imagine trying to predict the exact path of every single air molecule as it flows over an airplane wing. It's a mind-boggling task. To make sense of this complexity, engineers and scientists use mathematical models. One such model is thin airfoil theory, or TAT. TAT, as its name suggests, simplifies the problem by making a few key assumptions. First, it assumes that the airfoil is infinitely thin, like a sheet of paper. Of course, real airfoils have thickness, but this assumption helps to make the math more manageable. Second, TAT assumes that the wingspan of the airfoil is infinite. This eliminates the messy effects that occur at the wingtips, where air spills over from the high-pressure bottom to the low-pressure top. While these assumptions might seem unrealistic, they allow us to capture the essential physics of lift generation. By simplifying the problem, TAT provides a powerful tool for understanding how different airfoil shapes affect lift. It allows engineers to calculate lift and other aerodynamic forces with reasonable accuracy, especially at small angles of attack. At its core, TAT models airflow as two-dimensional. Imagine slicing an airplane wing from wingtip to wingtip, like slicing a loaf of bread. TAT focuses on the airflow over a single slice, ignoring any variations along the wingspan. To represent this two-dimensional airflow, TAT employs a clever concept called a vortex sheet. Imagine a thin sheet covered in tiny spinning vortices, like miniature whirlpools. These vortices, all spinning in the same direction, create a circulation of air around the airfoil. The strength and distribution of these vortices determine the lift generated by the airfoil. By adjusting the shape of the airfoil, engineers can control the vortex sheet and, consequently, the lift characteristics of the wing. TAT provides a mathematical framework for calculating the strength and distribution of these vortices based on the airfoil's shape and angle of attack. This allows engineers to predict how much lift an airfoil will generate under different conditions. Thin airfoil theory, despite its simplifying assumptions, has proven to be a remarkably useful tool in aeronautical engineering. It has been instrumental in designing more efficient airfoils and predicting their performance. One of the key applications of TAT is in analyzing the effects of flap deflection. Flaps are movable surfaces on the trailing edge of wings that alter the airfoil's shape, increasing lift at lower speeds during takeoff and landing. TAT helps engineers understand how different flap configurations affect lift and drag. Moreover, TAT is used to calculate hinge moments, the forces acting on control surfaces like ailerons and elevators. These calculations are crucial for designing the control systems that allow pilots to maneuver aircraft. The development of thin airfoil theory can be traced back to the early 20th century. Max Munkh, a German-American mathematician and aerospace engineer, laid the foundation for TAT with his groundbreaking work on airfoil theory. He introduced the concept of the vortex sheet and developed methods for calculating lift using potential flow theory. Later, Hermann Glauert, a British mathematician and aerodynamicist, refined Munck's work and extended it to include the effects of compressibility, which become significant at higher speeds. Glauert's contributions further enhanced the accuracy and applicability of TAT. Thin airfoil theory, a testament to the power of mathematical modeling, continues to be an essential tool in the design and analysis of aircraft. From the sleek wings of modern airliners to the nimble wings of fighter jets, TAT has left its mark on the world of aviation.